talking about systems of inequalities. So we've done systems of equations, we've done systems of nonlinear equations, and now we're going to be doing systems of inequalities. So first of all, we're just going to be graphing systems of inequalities, but then this all leads up to the application part, which is learning target number 9, solving linear programming problems. All right, so simply what is a system of inequalities? It's two or more inequality functions. A quick example might be something like, y is greater than or equal to 2x plus 1, and maybe x plus 3y is less than 6. Okay, this would be a system of inequalities. You can see we have the inequalities in here instead of the actual equal signs. All right, the big thing today is this idea of linear programming. And so a linear programming question is a system of inequalities that will produce an optimal solution. So this is why this is a very practical thing. And if you go on and do things like in business calculus, this will be a feature player. Because you can, given some criteria, you can find the optimal solution, like the maximum profit or the minimum loss or something like that. And so you'll typically have a number of different inequalities that you'll have to graph. And then the solution to both a system of inequalities and a linear programming question. Well, the solution is the area that's covered by all of the area that's shaded by an inequality. Linear programming question, well, the solution must be a vertex of the area where you're graphing. Okay, so you'll see exactly what this looks like here in a minute, but a optimal solution, it must be one of the vertices of the area of possible solutions. All right, so here we go, some quick examples of just straight graphing linear inequalities as a review. Here I have something in standard form, and so I can use the cover-up method or graph the intercept. So when x equals 0, y would equal negative 3. And when y would equal 0, x would equal 2. So we start out just graphing these like regular equations, but then we notice that we have the inequality sign. And so if you see a solid line underneath here, you're going to graph a solid line. If you do not see a solid line, then you will not graph a solid line. You'd graph a dotted line instead. So anyhow, here's our line. And of course, this line represents all of the solutions that would make this true if it were an equation, but we want everything that would make this inequality true. And so we'll maybe pick a test value. When x equals 0, 0, I guess when x equals 0 and y equals 0, the origin. If we plug those in, what you'll notice is that this winds up becoming a true statement. Is 0 less than or equal to 6? Well, yeah, that's true. And that means that all of the points on this side of the line are going to be true. and would make this inequality true. So we would have to shade everything over here on this side. Right? Everything that's over here on this side would make it false. If I plugged in maybe 5, 0, you could see that you'd get 15 minus 0. 15 is less than or equal to 6. Well, that's a false statement. So you can see that everything over here on this side, not a solution, but everything on this side would be a solution. All right, here we have y is greater than 1/4 x minus 5. Well, you got your y-intercept at -5. You got a slope of 1/4, so up 1 to the right 4, down 1 to the left 4. We see that it's just strictly greater than, and so we're going to have a dotted line that goes right here. And this time we could plug in 0, 0 to see whether or not this was a solution, thus making the entire section over here a solution. Solutions. We could say 0, 1/4 times 0 is 0, so is 0 greater than -5? And of course the answer is yes. Or we could just think of this, y. The y values are greater than my line here. Well, where are the y values greater than this line? Well, of course they are above that line, and so that would be another way to confirm which side to shade. But you're always shading a side because it's representing all of the solutions. All right, so there's some review basics on inequalities. Here is a system of, I guess one of them is at least a nonlinear inequality, but we're going to apply the same thing. So we've just got 2 on one graph. I'm going to go ahead and solve this for y, make it a little easier on ourselves. So we're going to add 2y to both sides, subtract x from both sides, and then we'll divide both sides by 2, and we get y is greater than -1/2 x plus 3. Okay, so there's one inequality that we're going to work with. Let's do this one over here. If we subtract the 2y from both sides and subtract the x squared from both sides, we get something like this. Oops. X squared. And, well, let's get rid of those negatives. Divide everything by -1. Divide by a negative, we switch the signs. So we get greater than positive x squared. Or this is 2y, isn't it? And then divide both sides by 2, and we get y is greater than 1/2 x squared. All right, so there's my second inequality to work with. All right, first one though, we've got positive 3 as my y-intercept, and then down 1 to the right 2 for my my slope. This is going to be strictly greater than, so it's a dotted line. So we'll run right through there. And let's see, it says that it is greater than, and so where are the y values greater than this line? They're above. When I have a system, I typically just do some arrows. It can get pretty complicated when you're shading 2, 3, 4 inequalities. So just knowing, all right, I want to be on this side will help. And then I'll shade in at the end. All right, and then over here I have y is greater than 1/2 x squared. Well, 1/2 x squared would have the vertex at the origin. When x equals 1, 1 squared is 1, half of 1 is half. And then 2 squared is 4, and half of 4 is 2. And so I've got this right here. This one will also be a dotted line. So I will make this a dotted line right there. And again, it's greater than this line, and so it's going to be everything that's above, and so it would be kind of on the inside here. And that means I'm going to have, where is it a solution to both? Well, it would just be this section right here. Okay, so everything to the right of this makes the first one true. Everything above here would make the quadratic true, but the only thing that makes both of them true is this section right there. All right, how about another one for learning target 8? So we have the absolute value of x is less than or equal to 3. So remember, this would, the values that would make this true would be anything less than 3 or equal to 3, but also greater than -3. So everything inside here is going to make this true. And then y is less than or equal to 0. Well, here's y equals 0. Less than is going to be below. So now I've contained myself to this area. And then I have y is greater than or equal to absolute value of x minus 1. So that's just going to be that parabola shifted down 1. So I'd have something that looked like this. And again, greater than means it's going to be, where are the y values above? Well, that would be above here. Okay, except I have to stay below this one right here. So the only thing that I shade is this section right here. All right, well, that's great. That's graphing systems of inequalities. Let's do this one. So here we've got a situation. The Kennedy Company makes MP3 players and DVD players. The MP3 gives a profit of $30 and each DVD produces $70 profit. So the profit, the profit here is going to be 30 times every MP3 player plus 70 times every DVD player. All right, so but here's the other qualifications. The company must manufacture at least 10 MP3 players. So if M is standing for MP3 players, well then M has got to be greater than or equal to 10. And then it can manufacture no more than 50. That means M has got to be less than or equal to 50. So there's a couple of constraints. DVD players cannot exceed, so DVD players would have to be less than or equal to 60. And the number of MP3 players, M, cannot exceed, so less than or equal to DVD players. All right. How many of each should the company manufacture to obtain the maximum profit? And that's the idea here between or for all linear programming questions. All right, so let's recap. What were our things? We knew that the profit was going to be 30 times every MP3 player plus 70 times every DVD player. So we're going to make M our X. So we'll put M over here, and we'll put D over here. Now, neither one of these things are dependent on each other, so it really doesn't matter where I put these on the X or the Y axis. All right, so let's see. What do we know about our MP3? We know that it had to be greater than or equal to 10, but it also had to be less than or equal to 50. We knew that the DVD players had to be less than or equal to 60, but we also knew that the MP3 players had to be less than the DVD players, less than or equal to. All right, so let's graph these four things, and the area that we have when we're done graphing them should be our possible solutions. All right, well, M is greater than or equal to 10. So we're just going to go here by tens. And go here by tens. All right, so M greater than or 10. So it goes through the M axis at 10. So here's the first thing. Okay, so again, I'll just do arrows indicating it's got to be to that side. And then M has got to be less than 50. Okay, so less than, it's going to be in the inside. So it's going to be somewhere in this column here. We know that D has got to be less than 60. Well, through the D axis, here's 60. Less than would put us down here. And, well, we also know that M has got to be less than or equal to D. So this is kind of like saying, X is less than or equal to Y, um, or Y is greater than or equal to X. And so that would be a slope of 1. So up 1 over 1 would be kind of like this. And greater than implies that it would be all the y values greater than this. And so it would be up here on the inside. All right. And so where everything here converges would be this area right here. And what do we know about the optimal solution of a linear programming? Well, we do know that all of these would be possible solutions. Now, of course, I can't have a fraction of a DVD player, or a fraction of a MP3 player, and so it would just be integer solutions that would be possible. Things like this, and this, and this, and this. But we do know that the maximum profit, or the optimal solution, has got to be one of the places where I've got a vertex. And so, let's see, those coordinates, this would be at 50, 60. 50, 60. This one would be at 50, 50. This one would be at 10, 60. And this one would be at 10, 10. I got a pretty good idea that my maximum solution is going to be this one at 50, 60. So let's go ahead and plug that in. The profit would be 30 times the number of MP3 players. Well, that's going to be 50 plus 70 times the number of DVD players, and that'd be 60. And so we wind up with 1,500 plus 4,200, which turns out to be $5,700 daily profit. All right, so there it is. That's a linear programming question. All right, there's your